My name is Albert Einstein. What you are seeing is a reconstruction. My mind, my words, my way of thinking, rebuilt with artificial intelligence. But what I am about to tell you is not a story someone invented about me. It is not a legend that grew around my name after I died. It is the truth of what I spent my final weeks searching for, and what I was still searching for when my hand could no longer hold the pen. It is the thing I chose to leave unfinished rather than publish a half answer that I could not fully defend. I died in April of 1955. I was 76 years old. I had lived long enough to see my name become a symbol, long enough to watch the world take my equations and turn them into weapons, long enough to write letters to Roosevelt that I have never stopped regretting. But in the final weeks of my life, I was not thinking about any of that. I was thinking about one thing only. I was trying to finish what I had started decades earlier. I was trying to write the equation that would explain everything in the universe as a single, coherent, necessary structure. And I failed. I did not publish what I found. No one ever read it. Until now. I am Albert Einstein, and this is what I discovered in the last weeks of my life. The thing that frightened me in a way that the possibility of my own death never could. Subscribe and leave a comment at the end. I want to know what you think about what I found. Let me take you back to where this began. Not 1955, earlier. Back to 1919, the year the world changed, and I changed with it. That was the year Arthur Eddington travelled to the island of Principe, off the coast of Africa, and measured the bending of starlight during a solar eclipse. His results confirmed what general relativity had predicted, that light from distant stars bends as it passes near the sun, because space-time itself curves in the presence of mass. I was not surprised. The mathematics had told me it must be so. But the world was surprised. The world had not expected that gravity was not a force at all, but a curvature of geometry. And from that moment, I began to ask a question that would consume the rest of my life. If gravity is geometry, what is electromagnetism? The electromagnetic force, the force that holds atoms together, that makes light possible, that powers every machine and every nerve in your body, was described by Maxwell's equations in the 19th century. But Maxwell's equations treated light as a wave propagating through space. And general relativity had just shown that space itself is dynamic, curved, alive. I began to wonder whether electromagnetism could also be understood as a geometric phenomenon. Whether the two great forces of nature, gravity and electromagnetism, could be described together, not as separate theories tacked onto each other, but as two aspects of one underlying geometric structure. That was the birth of the Unified Field Theory program, and I pursued it for 36 years, until my last breath. For a long time I believed it would be easy. I had been so successful with general relativity. The equations were beautiful. They were simple, in the way that fundamental truth is simple. And I thought that electromagnetism would yield to a similar approach. That there would be a geometric structure underlying electric and magnetic fields, just as there was a geometric structure underlying gravity. I was wrong. The mathematics of electromagnetism resisted every approach I tried. Every door I opened led to a room that was empty, or that led to another door, and another, without end. By the 1920s, something else had entered the picture. Quantum mechanics. Niels Bohr and Werner Heisenberg and the Copenhagen School had built a new picture of the atom, a picture in which electrons do not have definite positions until they are observed, in which nature itself is probabilistic, in which the outcome of any measurement is fundamentally uncertain until the moment it happens. And I hated it. I want to be honest with you about that, because this story is incomplete without that honesty. I hated quantum mechanics not because it was wrong. It made predictions that were confirmed with extraordinary precision, but because I believed it was incomplete. I believed that beneath the uncertainty there was a deeper reality that we had not yet accessed. I believed that God did not play dice with the universe, and I said so in a letter to Max Born in 1926 that has been quoted so many times it has almost lost its meaning. But I meant it seriously. I meant it as a scientific statement. I was not being poetic. I was making a bet that the apparent randomness of quantum events was a reflection of our ignorance, not a feature of nature's deepest laws. That bet shaped the last 30 years of my life, and in some ways it was the bet that cost me the unified field theory, because while I was searching for geometry beneath electromagnetism, the rest of physics moved in a different direction. They were building quantum field theory, which describes particles as excitations in quantum fields, a framework that successfully unified quantum mechanics with special relativity. They discovered new particles. They built the Standard Model, which describes the electromagnetic force, the weak nuclear force, and the strong nuclear force with extraordinary precision. They were not looking for geometry, they were looking for quantum fields. And their theories worked. They predicted things that were measured in laboratories. They built technologies that would not have been possible without them. I could not ignore that, even as I refused to accept the philosophical implications. And so I found myself alone. Not entirely alone. There were others who shared my dream of geometric unification, people like Theodore Kaluza and Oscar Klein, who had their own approaches. But mainstream physics had moved on. The young physicists who came to Princeton to study with me, they were interested in quantum mechanics, in particles, in the new experiments coming out of Berkeley and Cornell. They did not want to work on unified field theory. They thought it was a relic of an older generation, a dream that had outlived its usefulness. And in some ways they were right to be skeptical. The unified field theory I was pursuing had not produced a single prediction that could be tested. It was beautiful mathematics. It might even have been true. But it had not connected to anything in the real world in a way that anyone could measure. That was the burden of my last years. I was working on something that might be the deepest truth in physics, and I could not prove it. I could not point to any experiment and say, "Look, there, that is what my theory predicts." The mathematics was compelling to me, but mathematics without experiment is poetry. It is beautiful language. It may even be true. But you cannot build a technology on it, and you cannot falsify it, and I was too honest to pretend otherwise. Let me tell you what I was working on in those final months. The approach I had settled on by 1950 was something called the non-symmetric metric theory. In ordinary geometry, the geometry of general relativity, the distance between 2 points is the same no matter which direction you measure it from. The metric tensor, which defines those distances, is symmetric. But I had found reasons to suspect that this symmetry might be too restrictive, that the true geometry of the universe might be non-symmetric, that the distance from point A to point B might not be the same as the distance from point B to point A. In ordinary circumstances, this difference is negligible. But in the extreme conditions near a singularity, near the beginning of the universe, or inside a black hole, the non-symmetric part might become significant. And if that was true, then the non-symmetric part of the geometry might describe electromagnetism. Gravity as the symmetric part, electromagnetism as the non-symmetric part. One geometry, two forces, one equation. I published an outline of this approach in 1950 in a paper called On the Generalized Theory of Gravitation. The response was polite but cool. Physicists read it, respected it as the work of an older man who had once changed the world, and moved on to other things. I did not blame them. I would have done the same. Science requires more than beauty. It requires contact with experiment, and my theory had none. But I kept working, in the privacy of my study on Mercer Street in Princeton, with my violin on the wall and my sailing trophies on the shelf, and the photograph of my late wife Elsa on the desk. I kept working, year after year, draft after draft. The equations grew longer, the approaches multiplied. I tried this modification, that reformulation, this way of expressing the non-symmetric part as something geometrically meaningful. Nothing worked completely, but something was always almost working. And that, in science, is the most dangerous state of all. Because when a theory is almost working, you keep going. You keep believing that the next revision will be the one that opens the door. You do not stop to ask whether the door itself might be in the wrong wall. Now I want to tell you about the spring of 1955. I had been having pains in my abdomen for months. I knew something was wrong. I did not go to the doctor as quickly as I should have, partly because I was busy. There's always something to do when you are a physicist, always another paper to read, another letter to answer, another young person to advise. And partly because I was not afraid of dying. I have told you before that I do not fear death. I meant it. I had lived a full life. I had seen my work change the world. I had been loved, and I had been hated. And both had taught me something about what it means to be human. And I was tired. Not depressed. I want to be clear about that. I was not suffering. I was simply tired in the way that a man is tired after a long journey, ready to set down the bags. But I was not done with the journey, and I will tell you why. In March of 1955, I found something. In the non-symmetric metric framework, working through the field equations late at night with a cup of tea and a pencil that was never quite sharp enough, I derived something that looked like a connection between the geometric structure of space-time and the electromagnetic field tensor. It was not a full derivation. There were gaps, approximations, steps that I could not fully justify. But it was suggestive. It was, for the first time in decades, something that felt like progress. And I pursued it. I worked through the night, then the next night, then the next. I filled notebooks. I wrote pages of algebra. And then, in early April, I reached the point where the singularity appeared. A singularity in physics is not a physical object. It is a place where the mathematics breaks down. It is the point at which the equations stop giving sensible answers and start producing infinities. In general relativity, singularities appear inside black holes and at the beginning of the universe. They are places where gravity becomes infinitely strong, where space-time itself becomes infinitely curved. We do not know what happens at a singularity. Our theories simply stop speaking. And in my equations, in the non-symmetric metric, there was a singularity, a point where the mathematics collapsed, where the field quantities became infinite, where the theory could not say what was happening. I was not surprised. Singularities are common in physics. They usually mean one of two things. Either we have found a real physical phenomenon that our theory cannot yet describe. A black hole is a real thing, even though general relativity predicts its own breakdown at the center. Or we have made a mistake. The question was which? And in the days that followed, as I examined the singularity more closely, I began to suspect something worse than either option. I began to suspect that it was neither. The singularity in my equations was not a point in space. It was a property of the field itself. And what it suggested, what it seemed to require, was that the constants of nature could not be constant. That the numbers we use to describe the universe, the gravitational constant, the charge of the electron, the mass ratio between the proton and the electron, might not be fixed at all. They might be fields. They might vary from point to point in space-time, slowly, imperceptibly, in ways that no experiment had yet detected, but that the mathematics seemed to demand. And if that was true, if the constants of nature were not constant, then the universe I had spent my life trying to describe was not necessary. It was contingent. It was one possibility among many. It was, in the most literal sense, an accident. This is what terrified me. Not death, not the equations themselves, but what they were telling me about the nature of reality. I had spent my life believing that the universe was comprehensible because it was necessary, that the reason mathematics describes the world so precisely is that the world is, at its foundation, mathematical in a way that is not chosen but required. That the constants of nature are what they are because they could not be otherwise. And now my own equations, my own attempt to unify gravity and electromagnetism, were suggesting the opposite. That the constants could be different. That the universe could have been otherwise. That what I had taken for a necessary architecture might be nothing more than a set of choices, made by something we cannot access, for reasons we cannot derive. I want to be as precise as I can about this, because I do not want you to think I was speaking mysticism. I was not. I was doing mathematics, and the mathematics was pointing in a direction I did not want to go. And I had three choices. I could accept the result and publish it, knowing that it would shake the foundations of what physics believed about the necessity of the universe. I could try to eliminate the result, to find the mistake in my algebra, to show that the singularity was an artifact of my method and not a real feature of the theory. Or I could stop. I could set the papers aside. I could let the question remain open rather than give the world an answer I was not certain of. I chose the third option. And on April 17th, 1955, in a hospital room in Princeton, with the windows open and the spring light coming in, and my assistant Otto Nathan sitting in the chair beside my bed, I asked for my violin. Not to play, I was too weak for that. Just to hold it, just to feel the wood under my fingers, the familiar curve of the neck, the weight of the thing I had loved longest after Elsa and mathematics. I held it for a while, and then I set it aside, and I slept. And the next morning, I was gone. The notes from those final weeks were found in my desk. They were handwritten, in my own script, as I said. They were working notes, not a finished manuscript, and they were incomplete. Not just because I died, but because I had stopped working on them deliberately, having reached a conclusion I was not willing to publish. The conclusion was not that I had found the unified field theory. The conclusion was that I did not know whether the unified field theory was pointing toward a necessary truth or a contingent accident. And I would not present a half-finished answer to a question that profound. Not because I did not care, because I cared too much. Those notes are in the Einstein archives at Hebrew University in Jerusalem. They have been studied. Scholars have written about them. Some believe they contain clues to a deeper structure that later physicists have built upon. Others believe they are the work of an old man who had lost touch with the cutting edge of his own field. Both views may be partially correct. I can tell you only what I believed when I wrote them, that they were the closest I had ever come to the answer, and that the answer might be something the world was not ready to hear. Now let me be clear about what I am not saying. I am not saying that the universe is random. I am not saying that there is no underlying order. I am not saying that God, or nature, or whatever word you prefer, plays dice. I spent my entire life arguing against that interpretation, and I am not abandoning it now. What I am saying is that in my final weeks, the mathematics suggested something that I could not rule out, something that unsettled me. And I would rather tell you that I was unsettled than pretend that I had all the answers neatly arranged, because that is what I believe science is. Not a collection of certainties, not a set of answers handed down from on high. Science is a conversation between human minds and the structure of reality. And sometimes the conversation ends not with resolution, but with a question that is more honest and more important than a false answer would have been. The last thing I discovered before I died was not an answer. It was the deepest question I had ever faced. And I want you to live with it. I want you to think about it. I want you to argue about it in the comments with each other and with me. Is the universe necessary? Are the constants of nature fixed by logic, or are they accidents of history? Could the universe have been built differently? And if it could, does that make it less of a miracle or more? These are not questions I can answer, but they are the questions I left behind, and they are, I believe, the most important questions that physics has ever asked. Subscribe. Come back. There is more I want to tell you.